Hey everyone, welcome back to another video. In this video, we are going to do 15 limits problems together. And without further ado, let's get started. So for problem 1, we're going to have the limit as x approaches 3 pi over 4 of the function sine of x. Pause right now, I'll give you 3 seconds. Solve. 3, 2, 1. Alright, this is very simple. It's just a direct substitution problem. Because this function is continuous, so it'll just be sine of 3 pi over 4, which is just square root 2 over 2, or 1 over square root 2. Alright, problem 2. We're going to have the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, just by looking at it, we're just going to try direct substitution and see what happens, okay? If we plug in a 2 on the top, we're going to get 4 minus 4 over 2 minus 2, which equals 0 over 0, and that's indeterminate. So we're going to have to do something else and actually factor this function. So this is going to equal, so that's the wrong way to do it. This is going to equal, remember we know, it's a difference of squares. So a squared minus b squared can be turned into a plus b times a minus b. So we can turn this into x plus 2 times x minus 2 all over x minus 2. Now, because one factor is in both the numerator and the denominator, that means there's a hole in the function. So this entire function actually just behaves like x plus 2, except at the point at x equals 2, there's a little hole, and that's why when we try to calculate this limit, we get some indeterminate answer. So we can actually just cross both the top and the bottom, and we can get it's equal to the limit as x approaches 2 of x plus 2, which is just equal to 4. Problem number 3. Alright, it's going to be at the limit as x approaches 2 from the right of x squared minus 7x plus 10. I'll do a little line here to show it's a new problem. All over x squared minus 4x plus 4. Let's try direct substitution. Plug in the 2 on the top. We're going to get, and even though it says we're approaching 2 from the right, we can still try direct substitution. So it's going to be 4 minus 14 plus 10 all over 4 minus 8 plus 4. Yeah, that's right. Okay. That's going to give us 0 all over 0 again. It's indeterminate, so we are going to have to factor. So it would be the limit as x approaches 2 from the positive side of x. Let's see, what two numbers add up to negative 7 and multiply to 10? Well, that would be negative 5 and negative 2. So it should be x minus 5 times x minus 2, right? Because x squared minus 2x minus 5x plus 10 all over, and then this is very simple, x minus 2 squared. Alright, now we can cancel these out and change this x1 into a 1, so that'll leave us with the limit as x approaches 2 from the right of x minus 5 all over x minus 2. Now we can just directly plug in, and this will give us negative 3 all over 0. So as you can see here, this is why it's important that it's telling us to approach from the right. This is also indeterminate. And we can recognize this function to be a rational function, meaning that there's actually a vertical asymptote at x equals 2. So now let's think about this a little graphically. If the vertical asymptote is at x minus 2, that means that on one side of it, it's going to be approaching infinity or negative infinity, or they'll both be the same. They'll both approach the same type of infinity. So we actually, okay, as we approach 2 from the right, let's say we're at 2.1, okay? So at x equals 2.1, we're going to have 2.1 minus 5 all over 2.1 minus 2. So this is going to be a negative number all over a positive number, which is just a negative number. And because we're getting a negative number here, and we're very close to 2 here, you could keep doing this for more points that are closer to 2, like 2.01, 2.001, but you don't have to do all that. All you need to see is the sign of this value. As you're getting very close to 2, the output is still going to be negative. So this indicates to you that the function is actually approaching negative infinity. But technically it doesn't equal negative infinity, because any time you have a limit that goes to infinity, the limit does not exist. So this limit does not exist because it approaches negative infinity. It never reaches a finite value. So this limit does not exist. Alright, time for question 4. We're going to have the limit as x approaches negative 1 of the square root of x squared plus 3. Alright, for this one, let's try direct substitution. If we plug in a negative 1 into x squared, we're going to have negative 1 squared, which is 1, plus 3, which is the square root of 4, which equals 2. Now I know in the comments you could be saying it could be either plus or minus 2, but in this case we're only talking about the principal square root, because that's what the square root of 4 is. We're not solving a quadratic where it's asking us for all values of x. The principal square root of 4 is 2. Question 5, we have an infinite limit. So it's going to be the limit as x approaches positive infinity. Of the function x squared plus 2x plus 1 all over 3x cubed plus 2. Hey, I just realized I haven't been giving you guys a lot of time to pause it, but the pause it is now. Alright, now I'm going to solve it. Alright, if we try direct substitution, we'll see that we're going to have infinity squared plus 2 times infinity plus 1 over 3 times infinity cubed plus 2. That doesn't mean anything to us, okay? We can't possibly solve that. So we're going to have to employ either one of two methods. The first method, which is the most common at this point in the unit, is we're going to take this function, x squared plus 2x plus 1 over 3x cubed plus 2, and we're going to transform it by multiplying by a version of 1. Would you agree that if we multiply this by hold on, let me fix that. That's a plus 1. 1 over x squared divided by 1 over x squared. We're just multiplying the whole thing by 1, right? Because it's a number divided by itself, which is just 1. So this is going to turn into, well, if we distribute the x squared to both all these terms, it's going to be x squared over x squared, which is just 1 plus, or I'll write it out so you guys can see exactly what I'm talking about. It's going to be x squared over x squared plus 2x over x squared plus 1 over x squared all over 3x cubed over x squared plus 2 over x squared. And if we simplify this, it turns into 1 plus 2 over x plus 1 over x squared all over 3x plus 2 over x squared. Okay, now we can take the limit of this function. So this limit is going to equal the same limit as x approaching infinity of this new function. So 1 plus 2 over x plus 1 over x squared plus 3x plus 2 over x squared. Now the reason we do this, you might be saying, wow, why would we take all these long steps just to solve this problem? Well, now if we plug in infinity, we see using our limit laws, if we just look at the one on the top for a second, if you have the limit as x approaches infinity for 1, that's just a 1. If you have the limit as x approaches infinity of 2 over x, that's just going to be 0, because the bottom is just going to keep growing infinitely large, where this 2 is not even going to matter. It's going to be 2 divided by a super large number. It's going to approach 0, plus 1 over x squared. It's going to grow to be 0 even quicker, all divided by 3 times infinity. So this number on the bottom is going to grow very, 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 very large. So I'm just going to write an infinity as a placeholder. This isn't correct mathematical notation. I'm just going to place it there. And then plus another 0. These zeros we can just ignore. So it's basically going to be like 1 over infinity. This isn't correct. Don't ever do this on an AP exam as your reasoning. But just visually, you can see that it's going to be 1 over infinity, which is just 0. So this limit does exist, and it's equal to 0. Alright, actually, I'll write problem 6 like all the way down here. Alright, problem 6. Alright, for this problem, we now have the limit as x approaches -2 from the left of the absolute value of x. For this one, it's very, very easy. It's just direct substitution. We're going to plug in a -2 here. Absolute value of -2 is just 2. So that's our answer. Alright, we're going to have the limit as x approaches -2 of 3x squared plus 5x plus 2 over 2x plus 4. I'll give you a moment to solve that. Just pause the video. Just try some direct substitution. Okay, so plugging in -2, we're going to get 3 times -2 squared plus 5 times -2 plus 2 all over 2 times -2 plus 4, which is going to equal 12 minus 10 plus 2 all over 4 minus 4, which is just going to be 8 over, no, not 8. It's going to be 4 over 0, which is undefined, okay? That's not any value. So we can't directly substitute, so we're just going to have to factor this guy up here. So it's going to be the same thing as 3x. I know it's going to factor pretty easily. So that'll be a 1 and that'll be a 2. You know, just do, what is that acronym called again? I forgot. But 3x squared plus 3x plus 2x plus 2. That'll just add up to 3x squared plus 5x plus 2. And we can factor out a 2 from the bottom, so it should be 2 times x plus 2. Now, there's actually no factors that we can cancel out, but that's not a bad thing because we can see now that there's a vertical asymptote at x equals -2, and that's exactly the number that we're trying to approach. So we just know that there's gonna be a vertical asymptote on both sides. So let's actually take the limits from both sides. So first, we're gonna take the limit from the left. Okay, so the limit from the left is going to be the limit as x approaches -2 from the left of 3x plus 2 times x plus 1 all over 2 times x plus 2. So for this one, I'm just going to plug in a value that's slightly less than -2. If we do that, I'm going to have like, for this thing right here, I'm still going to have a negative number, because even if you plug in a -2, it's going to be -6 plus 2, which is -4. So it's going to be something even less than -4. So this thing is going to be just a negative still. If we plug in a -2 already into this right here, it's already going to be, look, -2 plus 1, which is -1. So if we make this x even smaller, it's going to be even more negative. So this is still going to be negative. And at the bottom, we're still going to have our 2 here. Now, originally, if we just plug in a -2 in here, we're going to have a 0. But if we plug in something even smaller than -2, like let's say -3, this thing is going to be negative. So far we have a negative times a negative all over negative, because 2 times something negative is still negative. And these cancel out, and we're just left with a negative. So this tells me that this limit is actually going to approach -infinity. But this limit does not exist. The limit does not exist. This is just a way of, describing its behavior at that point. That's why I write equals infinity, but just you have to know that limits that go to infinity do not exist. I'm going to write that down. Big words. Limits that go to infinity do not exist. Or D&E. So the limit from the left does not exist. We're just trying to, describe the behavior of this function. I want to see what happens if we approach the limit from the right. Is it also going to go to negative infinity, or is it going to go to positive infinity? So let's try that out. So the limit as x approaches to negative 2 from the plus is going to equal, of the function, 3x plus 2 times x plus 1 all over 2 times x plus 2. Okay, if we plug in negative 2, for this one, we're going to have negative 6 plus 2, which is negative 4. If we do something slightly greater than negative 2, we're still going to have a negative. As long as we don't make it too big, like an actual positive number. But if we make it, like negative 1.9999, we're still going to have a negative here. So I'm going to keep a negative here. All right. Now for this one, if we plug in negative 2 on default, we're going to have a negative 1. If we plug in something slightly greater than negative 2, like negative 1.99, we're still going to have a negative here. And at the bottom, we're still going to have a 2 here. And if we plug in a negative 2 regularly, for this part right here, we're going to be left with a 0. But if we have something that's greater than negative 2, we're actually going to have a positive, because it's going to be 2 minus 1.9999, which is still a positive. So we're just going to have a positive, because a negative times a negative is a positive, all over. 2 times positive is still positive. So we know that this is going to approach positive infinity, because the numbers are just going to get bigger and bigger and bigger, and the sign is going to be positive. But this limit does not exist. The only reason we did this, the only reason we took each one-sided limit, was just to give us a better sense of how this function is behaving. We know that they're not both on both sides approaching positive infinity. One's approaching negative infinity, and the other is approaching positive infinity. Alright, that was a long problem. Time for question 8. The limit as x approaches 1 of absolute value of x minus 1 all over x squared minus 1. First thing I'm going to try is substitution, but we see that we're just going to quickly get a 0 over 0. So next thing I'm going to try is factoring. So we can turn this, sorry, that's a bracket. It's going to equal the limit as x approaches 1 of the absolute value of x minus 1 all over x plus 1 times x minus 1. Now hold your horses at this moment, because it might be tempted just to cancel both of these factors of x minus 1, but we can't, because one's in absolute values and the other isn't. Okay, assume that we're only using positive values. If we're only using positive values for x, then these absolute values basically don't do a thing. I'll show you why. I'll start off with just a basic absolute value of x. Look, if x is greater than 0, then the absolute value of x is just going to equal x, right? Or whatever's in there. So if x minus 1 is greater than 0, which basically turns into x being greater than 1, then the absolute value of x minus 1 is just x minus 1. A key trick here is we just replace the x's with whatever our expression is. So if x is greater than 1, then this expression right here, absolute value of x minus 1, just converts back to a regular x minus 1. And you can see that our limits, we're actually taking it at 1. So this is very important. So in order to see what this limit is and to see if it exists or not, we're going to take each one-sided limit. So first we're going to start off with it being greater than 1. So we're going to start off by taking the limit as x approaches 1 from the right, because all the values we'll be plugging in and testing will be approaching 1 from the right, meaning it'll be greater than 1. So we can just actually transform this absolute value of x minus 1 into just regular x minus 1 because of this thing right here, because we showed that if x is greater than 0, then the absolute value of x is just x. And that's true. Look, if x is 5, absolute value of 5 is 5. There's no need for the absolute values. It's already positive. And if we're changing the expression to x minus 1, we just solve what x has to be greater for, and then we just plug it in here, and look, then it shows that this expression is just the base one. So at this point, we can just write x minus 1, because we're pushing from the right, of x plus 1 times x minus 1. Now we can cancel out these factors. So we'll have the limit as x approaches 1 from the right of 1 all over x plus 1, which is just going to be 1/2. Okay, So limit from the right equals 1/2. Now let's test out what the limit from the left is going to be. So the limit, oops, oh, I hate this, bro. Alright. Limit from the left of, now, if we're approaching x from the negative, well, let's go back to this example. Look, if x is less than 0 this time, then the absolute value of x is actually negative x. I know that seems very confusing at first, but I'll explain to you why. Let's say we choose -1, so x equals -1. I'll use a different number actually, because we're already using one in the other one. Say x equals -2. Then, what is the absolute value of x? Well, it equals absolute value of -2, which is what? Which is 2. And if x equals -2, then 2 must equal -x. So that's why that's the case. So now this time, let's say x minus 1 is less than 0. Well then, if that's the same thing as writing if x is less than 1, then the absolute value of x minus 1 is what? Is the negative of x minus 1. Because all we're doing is replacing this x right here, like before, look, absolute value of x equals -x, with just the x minus 1. So that should give us -x plus 1. Or we can just, keep it as -x minus 1. So now we can come back here, and we can rewrite this, because look, we're approaching we're approaching 1 from the left. So that means x is always going to be less than 1 itself. And look right here, this exact case accounts for when x is less than 1. So that's perfect. Oh, what battery is my friggin'... Alright, I got battery. Alright. So this is the perfect example. Look, so now we can transform this absolute value of x minus 1 into what? Negative of x minus 1, all divided by x plus 1 times x minus 1. These two x minus 1s cancel out, so we're just left with the limit, and I should have wrote in limit here too, but you guys get what I'm doing. Hopefully. Don't do that on your test. Of -1 all over x plus 1. We just plug in 1 now, so it's -1/2. So, as you can see, this limit does not exist. Because why? Well, the limit from the left does not equal the limit from the right. This limit does not exist. Alright. Time for problem 9. The limit as x approaches infinity of 2x squared plus 1 all over 3x plus 1 times x minus 2. Alright, we can't do direct substitution here because we have infinity. What I'm actually going to do is I am going to distribute this at the bottom. Why? Because we want to do that method from before. Now, one of the two methods. Remember, I talked about two methods you could do to do this. You could do the long, rigorous way of multiplying by a factor of 1, or you can just look at the degrees. You can find the polynomial with the highest degrees, and if they're matching in the numerator and the denominator, then you can just cancel them out. So I'll actually give you guys a shortcut for this. So we see it's just going to equal the limit as x approaches infinity of 2x squared plus 1. And you don't actually have to factor out this bottom, but I'm going to show you just for the sake of, explaining things. So look, it's going to be 3x squared minus 6x plus x minus 2. I'm literally just going to leave it at that. Actually, I won't. I'll be nice. So it would be limit as x approaches infinity of 2x squared plus 1 all over 3x squared minus 5x minus 2. So one great trick is, look, the degree of the highest term on the numerator is 2, and the degree of the on the bottom is also 2. So all I do is just do this, and I'll automatically know the answer is 2/3. Why? Because if we do that full-length trick from last time, the 1 over x squared divided by the 1 over x squared, we know that if anything has a degree that's less than x squared, then it's just going to go to 0. And these are going to cancel out to be just 2, because it's going to be 2x squared over x squared. Look, 2x squared over x squared. And this one on the bottom is just going to be 3x squared over x squared, it's going to simplify to 2/3 eventually. So that's the shortcut. Now, if the degree on the top is larger than the degree on the bottom, so let's say this was actually an x cubed next to this 2, then the limit's just going to go to infinity because the top's always going to be larger than the bottom at the very end of the thing. So, and the other way around, if the bottom has a higher degree than the top, then it's just going to go to 0 because the bottom is going to grow faster than the top. But when they're the same, then you can just find the ratio between the leading coefficients. Alright, time for problem 10. Alright, problem 10 is the limit. I've been saying limit so many times. As x approaches pi from the right of x over sine x. Okay, if we try to directly substitute, we're going to get a pi over sine of pi, which is 0. So we have to look at things a little carefully. So it doesn't matter what we plug into this, the top, we know we're going to get a positive number, right? It's just pi. And on the bottom, what are we going to get? Oh, and sorry, pi over 0, we're dividing by 0, and you know when we do rational functions, that's always the result, because we're gonna, in the process of taking the limit, we're getting numbers that are very, very close to 0. And when we take a number, a number like pi, and we divide it by something that's very, very close to 0, that thing's gonna explode up to infinity. So if we draw the unit circle real quick, bam, 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 we know that pi radians is right here. So as we get closer and closer to pi radians, what's happening to sine? It's 1 right here and it's 0 right here. So at this point, it's decreasing steadily from 1 to 0. So that means we know it's getting smaller, which is going to cause this top term to blow up, a positive number to blow up. But you can see here that it's not becoming negative. It's the lowest it can possibly be is 0. So it's still going to be a positive down here. So I know that it's going to blow up to positive infinity because it's going to be a positive number divided by, oh shoot, no. So it's going to blow up to a number that's very, very close to 0. So it's going to be a very, very small number. I'll do like a little small plus. And that's going to cause the whole thing to blow up to infinity. Because look, if we take sine of pi minus 0.1, we're going to have a super, super small number that's greater than 0, but very, very close to 0. Pi divided by, let's say, 0.000001, that's a huge number. And it's just going to keep getting bigger as you approach sine of pi. So that's why. Alright, so now what do we do in this case? Okay, I'm going to show you guys, I'm sure you can solve it a different way, but this is how I would solve it. I would actually factor this top into a difference of squares. So I would make it the limit as x approaches 1 of, we can make this a difference of squares of, something plus 1 times something minus 1. What is the square root of x? Square root of x. So I'm just going to call square root of x here, square root of x there. And this is actually different of squared. It's because it's going to simplify to x minus 1. And then at the bottom, we'll just have the square root of x minus 1. These cancel out. We're just left with the limit as x approaches 1 of the square root of x plus 1, which just leaves us with 2. So that's our answer here. Alright, question 12. We're going to have, and sorry I'm not doing a perfect job at explaining things. I'm not a great teacher, but I'm doing my best. Let me know how I can improve in the comments below. Let me know that, watch the video. Alright, for this next problem, we're going to have the limit. And you know what, for this one, I will change up the variable. We're going to use y this time. So we're going to have the limit as y approaches, oops, first time I use y, I mess up, Jesus. Alright, approaches 0 of what? Of sine of 3y all over tangent of regular y. So Roman, what are we going to do for this one? Well, if we try to just directly substitute, we're going to have sine of 0, which is 0, and tangent of 0, which is also 0. We're going to have 0 over 0. So in this case, we're actually going to turn tangent into we're gonna write it as sine over cosine. So it's gonna be equal limit as y approaches 0 of sine of 3y divided by sine of y over cosine of y, which is just gonna turn into the limit as y approaches 0 of cosine of y times sine of 3y over sine of y. So now I'm actually going to break up this limit now. I'm going to break it up into a product of limits. So I'm going to turn it into the limit as y approaches 0 of cosine of y times the limit as y approaches 0 of sine of 3y all over sine of y. Now automatically right now I could just tell you the answer, it's 3. But why? Well, I'll show you. Well, first of all, we know, well, I'm going to cross this out until I can actually show you. So we know that this limit, look, cosine of 0 is just 1. So this comes out to 1. We can just cross this out. We don't have to worry about this. The one we do have to worry about is the limit as y approaches 0 of sine of 3y over sine of y. So the shortcut is, if you have sine of something over sine of something and you know you're using a common variable, you can just divide both terms. So 3y over 3 is 3. And that's how I got 3 so quickly, but I'll show you why. So we're going to have to transform this this function into one of the foundational limits, which is, you know, sine the limit as x approaches 0 of sine of x over x, which equals 1. Remember that limit we proved using squeeze theorem? I'll actually prove it in the next video. But this is one of the limits you have to memorize, and I'll show you why this is the case in the next video. I just don't have time for today. This video is already, you know, like an hour long, I think. Okay, so we're going to have to, you know, whatever argument you have in here, you have to have at the bottom too. So we're going to have a 3 right here. So we're going to multiply by a form of 1 of 3y over 3y. So now we can rearrange things to get the limit as y approaches 0 of sine of 3y. I'm going to move this 3y to this side. And then I'm going to keep 3y over sine y here. So now I'm going to again separate each limit. So it's going to be the limit as y approaches 0 of sine of 3y over 3y. And the limit as y approaches 0 of 3 times y over sine y. I'm moving out this 3 just to make things more simple. So we know, because of the foundational limit from before, this just becomes 1 times whatever this is. This is a constant, we can just bring it to the front, so it's going to be 3 times the limit as y approaches 0 of y over sine of y. Now, as you can see, this has a very, very similar structure to the fundamental over here, except it's just inverted. So if we were to invert this function, and the answer is 1, it would just be 1 over 1, which is still 1. So this actually just equals 3. I know that doesn't make a lot of sense. You're just going to have to memorize these foundational limits. So this one and its more common form, this one. And I'll show you how we get those in the first place in the next video. I'm going to move like all the, oh shoot. Yeah, look at all this first of all. It's a lot of work, ain't it? Alright, I'll move here. The limit as x approaches, I'll try to make my handwriting neat this time. It's a negative infinity. I'll write that, negative infinity of 2x cubed plus 2 all over 3 x squared plus x. Right off the bat, I can already tell you this is going to approach negative infinity. Why? Well, before we're approaching a infinity, okay? And we see that the degree on the top is bigger than the degree at the bottom. If this were a positive infinity right here, if this thing right here were a positive infinity, then we could easily just tell this is going to blow up to regular positive infinity, because the degree on the top is bigger than the degree on the bottom, so it's going to grow faster, right? A cubic polynomial grows faster than a quadratic. And we'll actually go into that. We'll actually show you why when we get into derivatives later on. And we could also do the other method, where we multiply by, 1 over x cubed over 1 over x cubed. That's just the long way. You can just look at it this time. So we already know this is going to be bigger, but we're not plugging a positive infinity. We're plugging in a negative infinity. So as we plug in values into this x cubed term, it's going to be a negative times a negative times a negative, which is just going to end up being a negative. So in this case, it goes to negative infinity. So you got to check if you have an odd or even polynomial here. If this were an even polynomial, like if this were an x4 instead, if this were a 4, then it would be a negative times a negative times a negative times a negative, which would end up being a positive infinity. So you got to be careful on what kind of polynomial you have there. Oh, sorry, this was question 13. Hey, we're almost done. Alright, question 14. Second to last one. We're going to have the limit as x, I know, I'm just used to it. X approaches 0 of the square root of x plus x all over, you guessed it, x. Okay, that's a 0. Plug in a 0, we're just going to get 0 over 0. We're going to try to separate this expression into two expressions. Which, this is like a blind solve, okay? We're just going to try to do what we can. So we're going to break this up into the limit as the absolute value of x over x plus x over x, which will just give us the limit as x approaches 0 of, we're going to break it up into two. Oh my god, that is horrid handwriting. You see that? Absolute value of x over x plus the limit as x approaches 0 of x over x here, but that's just a 1. Okay? We're going to keep this one right here, and this time we know that this limit is just 1 because it's just a constant. So it's going to be 1 plus the limit as x approaches infinity of the absolute value of x over x. Not infinity. 0, 0, 0. Ooh, that's a big mess up. So it's going to be the limit as x approaches 0, not infinity, of absolute value of x divided by regular x. Okay, this is easy. Now we just have to solve what this limit is equal to. And in order to do that, we got to solve the limit from both sides. We have to find the limit as x approaches 0 from the right and the limit as x approaches 0 from the left. Now remember from the example from earlier, look, if x is greater than 0, then absolute value of x just equals x. If x is less than 0, then the absolute value of x equals negative x. And go back to the video where I actually explained why that's the case. So because we're approaching 0 from the right, that means that x is going to be greater than 0. So we can just simplify this to x over x, which just equals limit as x approaches 0 from the positive of 1, which is just 1. And this one on the bottom, remember, it'll be negative x, so it should be return negative x over x, which is negative 1, which is just going to be negative 1. Therefore, this limit does not exist because this one right here does not exist. So it's going to be 1 plus limit does not exist. The whole thing does not exist because the limit from the left does not equal the limit from the right. Alright, and lastly, 15. Limit as x approaches 1 of the absolute value of x times x squared plus 1 all over x.